Good morning. So it's been a while. It's been a minute since the last time I did a code walkthrough. This is going to be a little bit more than just a code walkthrough, though. I'm going to actually talk today about the use of AI in software development, which is something that I was a little skeptical of a couple years ago, and probably rightfully so because it was shit a couple years ago. But it's much better now, and so I'm going to show you a project that I've been working on that is almost entirely built with Claude Code, Codex, and other AI tools. I'm also going to talk about what's happening at work, um, and some of the conversations I've had with people from former companies who are also engaging in AI-based development, and kind of give you my views on what the future of this technology happens to be. So, with that, let's get started. A few months ago, I started working on a project called Argyll. Now, interestingly enough, I actually did have a project called Argyll, I think about 14 years ago. That project was actually just a simple JavaScript library um, that internally did the processing model that I'm about to demonstrate to you, but it was only for like JavaScript callbacks. And this was at a time before you had the await async await capabilities in JavaScript, and so doing concurrency was kind of a pain in the ass. It was like just a bunch of nested callbacks. I think was yield and generators at the time, but that was about it. So um, what you're looking at right now is the project. It consists of a Go backend, a React front end, and for storage, I'm actually using Redis. Sorry, and I'll explain why as we go. So, what is Argyll? It is a goal-driven orchestrator. It is not a workflow engine, even though this looks like a workflow. And what I mean by goal driven is that when you register a step, which is basically any RESTful service, it could even be a script, it could even be a subflow. The idea is that if you want it to do anything, it is not imperative. So you're basically not creating a flow with a specific starting point and a specific processing sequence and gates where it'll either go here because a condition was true or there because it wasn't true, and so on. Um, the way that it works is that steps get registered, and based on the input and output attributes of those steps, and you can see this one sort of standalone, it has no relationships, but based on those, it will automatically wire up a potential route for the the way that the orchestrator will process those steps. And so here, there are no goal steps selected, but what you can see is if I were to select, for example, notification sender, it will now highlight the steps that would be included in the processing if you were going to give it that as the goal steps. Now, one of the other things about Argyll that's really important is it will only do what it has to do in order to satisfy the goal steps. So, for example, as you can see, it tracks back to something called inventory resolver, right? And the thing about inventory resolver is it has an output that feeds into order creator, and then of course it goes all the way down into notification center. Now, if I were going to start this flow, for example, and I actually provided product info, which was the output that would have otherwise been provided by inventory resolver, then basically what you're going to get is, okay, ID, just call it blah, it doesn't matter. So as soon as that's satisfiable, you're going to see that inventory resolver is no longer part of the execution plan for that goal. So this is basically how it works. The idea is like whatever initial state that you provide it for processing, combined with whatever goal steps that you actually ask it to perform, it will only do those goal steps. And so I'm going to cancel out of here. And by the way, this is in Italian. I originally wrote it in English, but I've also added localization for the Swiss languages. So this is just for testing purposes. But this means cancel, and this means start. So here's another thing. You'll find this interesting as well. Is that yes, I could do that, but I could also say stock reservation, right? And the idea there is that now it's only going to try to use stock reservation as a goal. It won't actually go any further and trigger a notification sender as a downstream step. It's as simple as that. And the lines, like I said, these lines are automatically generated. There is no explicit relationship between these steps. The only thing that actually relates them are the attributes. Now, in a production system, like a real setup, the names, you might want to actually namespace them, because these are obviously too generic. So you could actually have them like prefixed by a domain or whatever, however you decide to model these things, and so it would be able to wire things a little bit more precisely. But for demonstration purposes, this is how it's actually done. Now, if you go into the editor, if you double click, you get the editor for a step, and what you're going to see is that every step has an actual ID. It has a name, which is like just the friendly name. Then it has the attributes for that step. And you've got your input attributes. You've got here an optional. And the idea there is that if there's an upstream provider of that value, then that's what it's going to use. But otherwise, it will default to whatever the default happens to be. And then you have your outputs. The attribute types, they're your typical JSON types for now. In the future, I might add JSON schema or something else where you can define, legitimate structural types. But right now, it's just that. It will do the checking though, so that's actually important. Now, going back to the attribute thing, like I said before, if you look at the way things are processed, it looks like a directed acyclical graph. And the question is, well, how do you guarantee that? Well, so if I were to actually create a cycle based on the attribute names, because it's only about the attribute names, and I tried to either create this step or initially register the step or update the step, then it will immediately boot it out as saying this would result in a cycle. It's an unacceptable condition for a step to actually be in, so it won't allow it, no matter what. So you'll never see cycles in the execution plan. Going up to the step types, because this is where it kind of gets interesting, right? So you have synchronous steps, and what a synchronous step is a standard HTTP RESTful call. It's not doing full mapping. Like, you can't just take any RESTful service and provide things to it. The way that it works is that you're basically posting to a service and getting a JSON object back, and you're posting a JSON, of course. Then you have async, and the way that async works is it is basically an HTTP synchronous call, but it also provides to that service a webhook URL. And the idea then is that the synchronous call itself immediately should succeed or fail if it can't deal with the request. And then eventually later on, what ends up happening is it will call back to the server with the webhook that was provided and actually fulfill the request. Now, this can go on forever, right? There, you can set it up so that it can time out after months, and the service will allow for that. Next, we have scripts. Now, scripts are going to be in Ale, which is the language that I talked about a couple of years ago here that I've been working on. It's basically a scheme, or Lua. It comes down to preference at the end of the day. What I would say is that Lua is very sandbox, so there's no local system access. You're basically using it for glue code and doing checks and stuff like that. I'll show you what I mean, because there is actually a script. But before I do that, there's also the idea of a flow. And so a subflow is pretty much choosing goal steps, right? And saying, hey, for this subflow, my goal is to actually result in the notification sender. Here are the attributes that the outer step takes. And then also what you would end up doing is you would map those to the potential input steps for that. So, input attributes, sorry. And the cool thing about that is then you can basically create more complex subflows. And when that subflow is done, it will actually report to the parent that it has completed. Important to understand is that it's a subflow is not sort of a singular thing. It's actually potentially a lot of things. So one of the things that you'll see here is that if you give an attribute an array type, you all of a sudden get an option of like singular processing, meaning the entire array is provided to the step as is, or multiple processing. And then what that means is that the step executor will take that array and iterate over all of the values of that array, and it will execute the underlying flow that many times with the input provided to it based on the singular array element. If you have multiple, it will create a Cartesian product and it will process the entire Cartesian product. That's how the processing model works. It's not just for flows, actually, it's for any step. You can actually do this sort of for each capability. Going back to the scripts, what I'm going to show you is here's a script. So this is basically a script step, and it's written in Lua. And what you can see is that we've got our attribute mapping. So we've got age, credit score, income, eligible, and then those just become eligible is an output. Sorry, those just become variables inside the script, right? So age, that'll be provided based on the script. And then on return, you're just returning a table. In Lua, I think it's called a table, based on those values. And then that triggers the downstream processing. Just to give you an idea, I'm just going to run it so you can kind of see what one looks like. So just going to run it. I'm not going to give it any init state. And then as you watch, it's actually running these two steps in parallel because it can. They don't have any dependencies on each other. So it can happen. And once they're both done, because they're providing downstream attributes, this one will start running. And once it's done, it's going to trigger both of these. And the reason why is because these are independent of each other. They can run in parallel. So eventually it'll finish. This is a webhook, by the way. So it takes a little longer. And also the timing here is completely synthesized so that you could sort of see how it would actually operate in the real world where services are taking longer. And the only reason that I did it like that is just because otherwise the flow would immediately finish. This processing engine can do about 7,000 flows in 1 second on my M2 MacBook Air. So it's not slow. And then what you can see is that both of those finished. And then downstream, it will finally finish the notification sender, which was the goal. You've got multiple flows that you can find, and then you can search for them based on names. There's no requirement that they have to be auto-generated names. You can give them any name that you want, any ID that you want. Sorry, but that's it. That's what the flow happens to look like. If I were to go into what the Redis data for this looks like, this is where it might become interesting. I don't know. What you're going to see is essentially events. And so let me see, what was this one? 419. So that was 419. Let me find it. There are the events. Basically, Argyll is completely event sourced, and it uses optimistic concurrency, meaning that the way that events find their way into Redis is an optimistic append of events. What does that mean? So the idea is that you would execute against your current understanding of the state of a particular aggregate. In this case, it would be the flow itself. And you would apply events based on the state transformation target that you have for it. And then at the end of that, what it's going to do is going to take those resultant events that represent the state transition that you applied, and it's going to try to send them to Redis. Now, it does that with an atomic Lua script. So the good thing about that is that you will send them all at once. If Redis decides that it can't because there's a version conflict, meaning that somebody else has written to that append point in the meantime, it will just kick it out and say, no, you can't do that. And what that means is that going back, Redis will provide all of the delta events, meaning the events that have actually been appended in the meantime, so that the execution processor and the server will apply those events. And it's almost like a rebasing Git, right? It'll apply those events, and then it'll try to execute the command again based on the new state until you eventually have everything fully committed. That's basically the way that the model works. For flows, it actually works really, really well because flows have very little contention, so you're not having to do a lot of retries, and so you'll end up with basically this, just a bunch of events. These are all events generated by Argyll to describe the transition of the workflow. I don't want to call it workflow, the flow state or the orchestration state of any single flow, and this is the flow that you just saw. And like I said, it's very fast, mainly because it's using Redis, but also I've tried to write it to be rather fast, because there's so little contention on flows. Because this can run, distributed, the flows themselves actually execute pretty quickly. The engine itself, there is a lot more potential for contention because it's sort of maintaining the entire world state. So that's handled a little bit differently, but it's still an event-sourced approach. One of the things you're going to see is that some flows only have events, like the one we're looking at right now, but there are other flows where we've actually created snapshots. And there's a heuristic rule about how snapshots work in this, is that if you try to load events, meaning like you've never seen that flow before, it may be originated in a different system, or the system has actually restarted in the meantime and it doesn't have any local cache. What it's going to do is it's basically say, hey, here are all the events. There is no snapshot right now, and it's going to basically create a snapshot based on a very simple algorithm. I think, as I recall, the way that I did it is that if the events combined, the size of the events is more than half the size of the projected state that might otherwise become a snapshot, then it's going to create a snapshot. So it'll continuously do that over time. The idea there is that snapshots don't actually themselves, they don't grow unbound, especially when it's like a flow or something like that. And so this is kind of a good, guess as to the best way to optimize whether or not to actually create a new snapshot. So it tends to work relatively well. Of course, the sequence part of the snapshot, this is the actual event that the snapshot represents, meaning like this is based on the first 33 events that were actually appended. And what it can do then is say, well, I got a snapshot. If you request it, it'll give you the snapshot, and then it'll only give you events 34 and up, meaning the delta, so that you're also not receiving all of the events because you don't need to project all of the events. That's basically how that works. All right, just to dive in a little bit more. So the code, project's getting pretty big, but the code is Go. These are helpers. Hold on. I should have been prepared for what I was going to show today. Actually, don't even. Let's not even do that. So the code's written in Go, the back end. It's broken into multiple things. So there's the engine itself. It's only responsible for the actual processing. And then there's an archiver. And the reason why there's an archiver is because, Redis is memory bound. Even if you're doing database dumps and you're doing like write-ahead logging with Redis, which I highly recommend because you don't want to lose data, it's still memory bound because the working state of the system will continue to grow. And so there's also policy for being able to take all of the deactivated flows and send them through an archiver. And there are a couple of different archivers, and the idea of the archiver is it's just constantly monitoring the state of Redis. There's a stream and just pulling things that need to be archived. And so it will just take that stream and send it to whatever archiving persistence that you've decided to use. By default, in the Docker Compose setup, it's dev null, so it sends it to a file. But there's also a blob archiver where you can just send it to S3 or Azure or GCP, making it pretty easy to actually archive your stuff. Now, why would we archive deactivated or completed flows? Mainly because it's important to understand that this is not an engine of state, right? The idea here is that we're not running flows in order to accumulate state and then treat that state as authoritative. The whole purpose of the orchestrator is to orchestrate, right? Its only job is to run a service based on some information that comes out of that service, use that in order to determine how the rest of the flow actually executes, and that's it. And I've seen quite often that BPMN engines and even other orchestrators end up becoming this sort of cumulative state. That is not how Argyll works. Argyll really is just a pure orchestrator. You've got your snapshots. If you really want them, you can use them. But you don't. It's not actually recommended. But the data is kept around forever because you might need an audit trail. You might need to look back at the events that have actually occurred in order to determine what the hell happened. Right? you need that auditability, so it's there if you need it. But otherwise, you could just pipe it to dev null and it's just disappeared at the end of the day. So this is one of the other options. Now the engine itself it's the code is not that complicated, quite honestly. But I think it's probably worth getting into the AI aspect of it, because I think that's the more interesting part of the story. And just so you know, I have arthritis. I also really like to play bass. So yeah, I've been for a couple of years actually wanting to write this orchestrator, and the pain in my fingers has kind of kept me from really seriously considering it. It's because I'm older, and I would rather cause pain to my joints by playing bass than by coding at this point. It's also a big thing. So from my point of view, my brain works perfectly fine. I know exactly how I wanted this thing to be implemented and how I wanted it to run and sort of play out. But I knew that from a coding point of view, it would be laborious and painful and just take forever. So I decided that, all right, fine, I'm just going to give Claude Code a try. I had worked with GitHub Copilot and stuff in the past. I was never incredibly impressed with GitHub Copilot and AI-based autocomplete. So Claude Code for me was a different take. And let me kind of describe how that went. So at first, it was really difficult to change my mode of thinking, because I'm very used to sort of the imperative approach, right? It's like I code this thing to produce this result that I'm trying to achieve, and that works fine. But what I noticed happened was that Claude would basically, especially at the very beginning, try to one-shot everything. And that resulted in a massive amount of code that seemed to work, but didn't work quite well. And one of the good examples I can say is I said, hey, Claude, I gave it a pretty decent spec, like exactly how the system should run. And I didn't get into implementation details. I really tried to just describe kind of the properties that the system should have after the fact, but I didn't get too into some of the non-functional requirements, and Claude just made a lot of assumptions. So for example, the initial cut of this thing was incredibly slow. It could do about, I think, 250 flows per second. And Claude thought that was perfectly okay. And then, when you look at the code, which I hadn't really gotten the discipline of really kind of verifying and validating everything Claude's doing in a very incremental way. I'll talk about that afterwards. But then when you looked at the code, the way that the processing model worked was that a flow would be created. It would go into a global memory pool of the various flows that are currently running. And Claude would have a type loop where in that type loop it would say, hey, flow A, do you have any work? Flow B, do you have any work? Flow C, do you have any work? Literally, it would basically round robin through every single flow. Even if the flow was completed, it didn't care. It just basically looked at every single one. Do you have any work? And made it incredibly slow. It was like a choke point, because Claude, here's one of the things that I found. If you if you create a corpus of knowledge to draw from for an LLM that is based purely on the public internet, you will very quickly find that the quality of the solutions that it produces is limited by the quality of the code that is in the corpus of knowledge that it drew from the public internet. So while Claude is really good at talking about concurrency, it is really bad at implementing it. Very, very bad. I've had, even if I've created Claude rules throughout the process of building this thing, I've constantly had to remind it of how event sourcing should properly work, how optimistic concurrency works, how the CQRS pattern works. I've had to continuously tell it that this is how it should happen. And no matter what rules you actually provide or what guidance you provide in like the Claude MD or any of like the breakout rules, it just doesn't get it. So I quickly ended up having to retrain myself. And just go really, really small, really, really iterative, and sort of get back to like the TDD approach to software development, where I was literally starting off with like a spec, meaning some verifiable thing that I wanted Claude to be able to change in the code, or some kind of gherkin-like functionality that I wanted to be able to describe for it to execute on, and let it do that. And then things started to get a lot better. Now, how was it able to get to the point of performance where it is now? That was basically me having to do traditional normal engineering and profiling and saying, listen, this is not working. There's too much contention here. There's too much locking here. You don't need a mutex for this. It's not necessary, and so on. And I guess the lesson here for anyone who's even thinking about using AI for coding is that AI tools are going to amplify what you bring to the table. So, and what I mean by that is that, if you come to the table with an engineer's hat on, like with the discipline of a really good software engineer, then Claude Code in your hands is like scalpel in the hands of a really gifted surgeon. Okay, if you are some dude who thinks that this is like vibe coding all the way, it is going to amplify the fact that you are not an engineer and you have no idea what you're doing. It's as simple as that. And that might change in the coming years, but I have a strong feeling that it probably won't. And why I say that is because, we have kind of a confirmation loop now, right? Claude is drawing all of its knowledge from publicly available code. Any of the code that gets back into the public domain is very quickly being kind of overwhelmed by Claude generated code, meaning that the bar overall is not going to raise. And the only way that it will raise is if the engineering discipline basically continuously raises the bar of the content that's being produced, and finding its way back to the public internet. Otherwise, it's going to be kind of a downward vicious cycle of just garbage, like garbage piled upon garbage, right? So engineers are still necessary. Engineers are going to end up having to just inject novelty into what they're doing and good engineering so that we can sort of combat this sort of downward potential trend or gravity toward just increasingly poor code that becomes part of the model. It just keeps feeding back into the model. So your job is not in danger, but I will say that unless you learn these tools, your job may be in danger. And the main reason is because it is a game changer. It is a productivity game changer. For me, these tools, the only time in computing history that I can compare to them is when software developers went from doing punch cards and then having to feed those punch cards into like a tray to be read by the machine and then wait for the batch processor to run them and then come back like the next day to see if the program ran, to going to actually having like a terminal and a keyboard. Like that was a major game changer in productivity. I think we're looking at the same thing right now. Everything changes, and I don't think it ends here. I have a strong belief that over the next 5 years, code, which quite honestly is mainly a means to an end, to be very honest, it has always been a means to an end. It's been an abstraction that we use to be able to describe what we want the machine to do. I think code is also going to fundamentally change. I think it's not going to matter anymore. We will end up talking to the AI and describing the properties of the system that we want to produce, its functional, non-functional requirements, and not necessarily seeing code, because code won't matter. I have also a feeling that the feedback mechanism that the AI tools will provide to us will start to better resemble like P code. And what that means is that our jobs are going to change, right? We're not going to be so-called coders anymore. And if I'm being entirely honest, about 10 years ago, I stood in front of a bunch of my developers and I told them to their faces, I don't care about your code. I only care about the outcomes that you produce for the company. If you can generate those outcomes without writing code, or even better, deleting code, that is actually ideal. That's preferable, because the goal of software development is to achieve the outcome that you're trying to achieve, not to create sort of a massive proliferation of code, because every line of code is a liability or a potential liability to a company. It's something that somebody has to maintain and so on. So, get that code thing out of your mind. Code's gone. We're not programmers anymore. We're now architects. Everyone is going to end up being an architect. We're going to think about things in terms of systems, either systems in the large, systems in the small, and how those parts of the system actually interact with each other. We will have to think about things in terms of like, how do you structure these systems in a way that's more amenable to creating good outcomes with the AI tools. Like these are the things that are going to end up changing. I strongly believe that. It may be that there are different platforms, because there are going to be different ways to actually implement systems. That doesn't go away. But the languages themselves, they're not going to matter as much. The beauty of code, I mean, it's interesting to me because I code in Go, right? And Go is not beautiful. Go is actually utilitarian, Spartan, and ugly. And I think it's intentional, right? The idea is like, you're going to write the code usually once and read it a million times. It should look as stupid as possible so that there's no magic to it. There's no confusion as to what the hell you're actually reading. And I think we're going to go even further down that path. It'll be something that is like an abstraction, that the ergonomics are more meant for readability than for writability. And I have to tell you, like, my way of coding over the last 5 months has gone from me inputting code and not worrying so much about reviewing it because I was part of the loop of creating it, to me basically reviewing code. So, now my almost all of my interactions with code are reviewing the code that Claude generated. And what that means is that the only interaction being reading means that the way that it's presented to you is the friction point, and that will also have to change in order to sort of facilitate the best ease of being able to read and validate that code. So it's going to change. You're going to have code that is not designed for input, it's only designed for output. That's going to happen. I can guarantee you it's going to happen. So get ready. I mean, it's one of those things where it's a sea change. If we don't adapt to it right now, then honestly our careers are in jeopardy. And listen, if you had asked me this like 2 years ago, I would have said, nah, we're always gonna need to code. No, I don't agree anymore. I've changed my mind. We're always going to need engineers, but we're not always going to need to code. We're not. These tools are going to get better. Do I think that they're going to get 10x better? No, because I do think that they're limited by what's out there. And we're always going to need engineers who can fight what's being generated by the code and can verify it, and not the code, by the LLMs, and can verify it and make sure that it's actually sort of up to snuff. It reminds me a little bit of a talk that Uncle Bob gave a while back. I can't remember the title of the talk, but essentially what he said is, he was talking about engineering, like historical engineering, like building bridges as a discipline, I think. Um, and then he talked about the fact that, if an engineer designs a bridge and the bridge collapses, then they will be disciplined because there are regulations around how you actually build those structures. Right now in software development, there are no such regulations. There's no regulatory body for how we do it. And what Uncle Bob said is that if we don't become more professional, if we don't get highly disciplined about the quality of the code that we produce, then we will be regulated, and it'd be better if we just regulated ourselves, so we don't have to have outside regulators do it. Because once the outside regulators do it, things become not as much fun. So what I'm going to say now is that with this AI boom that's happening and AI generated code, it becomes even more important that we have a strong eye toward the quality of what's being produced and making sure that it is actually not going to cause a bridge to collapse or result in death, because the regulators will come if we don't. And what I can tell you right now is that when that regulator comes, or when the police come to ask you why this happened, they won't buy the excuse that Claude wrote the code. Someone's going to have to be accountable. So we do have to become more disciplined with these tools. Anyway, so this project, I'm pretty happy with it. About 95% of it has been written by Claude. I've definitely given it a lot of input about how it should format things. The one thing that I would say is that the way that I've approached it is different than the way that bigger teams or companies have approached it, and I think that that's actually necessary. So, like, for a project in the small, it's totally okay to sort of just cowboy it. I don't have very many rules, for example, in my Cloud MD, right? It talks a little bit about the project and its purpose. Here it's talking about the event sourcing implementation, and what the rules are and how it should go down when you implement new features against that system. Go style guide, right? Markdown style, and then how TypeScript should be written. Not much. I mean, it's really there's not much more to it than what I've produced here. I've got a lot of docs, of course, so its docs are generally okay. But what I can say is that the company I'm working at right now, they are going pretty heavily into having like really big repositories of how code should be generated, how tasks should be taken out, how testing and agents should work, and stuff like that, which I think is important. I think it's actually necessary, because, again, going back to that quality thing, like, we have to ensure this quality, because otherwise we will be regulated. So if companies and teams are being really proactive about sort of creating like a safety scaffold around what they're doing, and creating like high productivity tasks and stuff like that, then all the better. In my case, I like the personal interaction. I like iterating. I like going back and forth and sort of finding my way. And I think with AI, we're still finding our way. In fact, with software development in general, we're still trying to figure this thing out. It's been since like the 60s, and nobody could decide on what the best approaches to software development were up until a couple of years ago. We're still in the same boat, right? So we're still figuring this thing out. But what I would say is that this is a game changer. So learn it, get good with it, because it's going to matter. It's going to matter in your career. I would also say, as things change, adapt to how they're changing. It's going to be really, really necessary. I think you'll find that you kind of feel, I don't know, I'll say how I felt. I felt kind of disconnected from the code. I think in my mind, I really liked coding. So I have had moments where I felt like, am I even coding? Do I even know how to code anymore? And when you go back, what I've noticed is, like, when I do have to code things manually, because sometimes I do, I do think that the back and forth with the AI has actually made me a better thinker about code. So I'm thinking far more about the quality of the code, far more about the structure of the code, I'm being far more critical of what's being written, and it's making me better coder as a result. But of course, all the behaviors have had to change, meaning I now am just doing code reviews all the time, which is fine. I'm totally okay with it. I'm senior enough that I had already gotten into sort of that mode of operation anyway at work, so it's fine for me. Um, anyway, I think that's it. Um, the nothing to add, people. But yes, seriously, dive in, learn this stuff. It's important, and have a good one.